Today's topic is transition state theory, which is also known as activated complex theory. For this purpose, let's take an example in which consider two substances A and B, which are linked by a simple unimolecular elementary reaction in which Kf is rate constant for forward reaction and Kb is rate constant for backward or reverse reaction, and the system is in equilibrium. And according to Arrhenius equation and potential energy of the surfaces, an expression given as equation number 1 is derived from the Arrhenius equation, in which this exponential term is abbreviated as activation energy. Here it can be explained as the potential energy diagram versus reaction coordinate, in which this internal energy is the change in internal energy from going from one of the minima to the maxima, which is called the transition state or the activated complex. When enthalpy of activation or activated complex is expressed in terms of internal energy, we get an expression that is here the activation energy plus work done. As the work done is almost negligible, near to zero, this activation energy is equal to the enthalpy, and these plus plus expression denote the contribution for the activated complex. So using these terms, the Arrhenius equation was developed to A into and if you multiply this term with exponent of entropy over R into with existing exponential term, that is delta H plus plus over RT. So these two terms can be rearranged as so we get another constant. It is abbreviated as A dash, and with exponential form of change in free energy So this is how equation number 1 was derived from the Arrhenius equation. So here this delta G is the standard free energy of activation. So this equation is an empirical generalization of the reality. And the activated complex theory is also based on the Arrhenius theory, which is based on the idea that reactions proceed through a fairly well defined activated complex as shown in this figure. Here this energy is energy for the reaction, which is actually a difference of minimum energy required for the forward reaction versus minimum energy required for the backward or reverse reaction. For a reaction, we must supply the energy to proceed the reaction. We are focusing on the unimolecular reaction in which species A and B is in thermal equilibrium. For this system, free energy is changing during the reaction, and the activated complex is the configuration of the maximum free energy. So using the expression derived from the Arrhenius equation, that is written as equation number 1, we can derive the values for the rate of forward and rate of backward directions, and the value expressions for the rate constants of forward and rate constant of backward direction using the activated complex theory. So using equation number 1, we can write the expression for the unimolecular reaction given here. The concentration of activated complex, that is the state of maximum energy with respect to concentration of species A, that is equivalent to the exponential term that is derived from the Arrhenius equation, that is written as equation number 1, this one. So here this free energy is for the forward direction RT, and the constant A is expressed as gamma A over gamma plus plus. Here gamma A is activity coefficient of A, over activity coefficient of activated complex. Similarly, for the backward direction, we can write the modified expression derived from the Arrhenius equation, that is expressed as concentration of complex over concentration of species B, that is equal to the exponential term in which gives free energy of the activated complex for the backward direction, and the activity coefficient of species B over activity coefficient of activated complex. So this equation is equation number 3. As we know that the activated complex is a transition state, and which cannot be measured using usual means. For this situation, the concentration of complexes can be calculated from the standard free energy of activation according to the equations, equation number 3 and equation number 2. The activated complex is actually formed from species A that is reverted to species B. So this intermediate state, once created, that it must be go to species B when the reaction is forward, and it may revert to species A when the reaction is reverse or backward. So we have four types of fractions of molecules, in which first one is A, that is reverting back to A after formation of activated complex, so the fraction will be FAA. Second is A is converting to B, the fraction of molecules will be FAB. Third condition is B, that is reverting to A, here fraction of molecules will be B, species B is reverting back to A. And the fourth one is B is reverting back to species B after formation of activated complex. So the net rate of transferring A to B, it is written as forward reaction. So the equation is rate constant for the forward reaction into concentration of A, that is equivalent to the fraction of molecules A which are reverting to B, and here we can write K dash, a combined rate constant into concentration of complex. So here we get equation number 4. So next is net rate of transferring B into A. So it is a backward direction. For this system, we have rate constant of backward direction into concentration of species B, that must be equivalent to the fraction of species B that are reverting A into a combined rate constant and the concentration of activated complex. That's equation number 5. As we have discussed that the system is in equilibrium, the rate of forward reaction is actually equal to the rate of backward reaction. And for the system, the fraction of molecules A which are reverting to B is equal to the fraction of molecules B which are reverting back to A. It means that we have a probability of the activated complex. Half is the probability for the species converting to B, and the half is probability of the species which are converting to A. For the simplest system, the conversion of A into A, or we can say the B is reverting back to B, is considered as 0. It means that the complexes are not considered as reverting to the source states. Instead, any system reaching the activated configuration is transmitted with the unit efficiency into the product opposite to the source. So for the simplification, the constant, this fraction of molecules will be divided to small k over 2. Here k is equal to 0 to 1. That is also known as transmission coefficient, which is also based on the reversion of the species to the source states. So according to this consideration, the equation number 4 and 5 are modified as rate of in which the fractions of the species are replaced by constant known as transmission coefficient. Now rearrange this equation. Here Kb is equal to K half K dash concentration of activated complex over concentration of V. So by comparing this equation number 3 having an expression of free energy and the expression with the rate of backward direction, expression for the rate constant of forward and backward direction. Here K dash is equal to 2 kT over H, where K is the Boltzmann constant and H is the Planck's constant. So overall this equation is simplified as exponent of change in Gibbs free energy over RT. And this equation holds at equilibrium and also away from the